Good morning, everyone. I am Belal Hossain, a civil engineering grad student of University of Maine. Today, I am going to present Project 2.9 under Research Thrust Area 2, and this project is supervised by Professor Aaron Gallant and Professor Ward Darshan. Now, I would like to talk about a large-scale demonstration of soil carbonation that has been conducted recently, where we have obtained some exciting results to share with you all. Before I jump into the talk, I would like to mention a brief background of the project and how we landed into this larger scale experiment. So, for any civil infrastructure development, challenging subsurface conditions demand ground improvement or soil stabilization. In that case, chemical stabilization, for example, cement or lime stabilization is one of the most common technique that adopted by transportation agencies and state DOTs. However, these conventional methods, especially lime stabilization, to create the binder to obtain desired strength and stiffness is a time-consuming process. On the other hand, both cement and lime production is associated with very high CO2 emission during their production phase. That's why this project is proposing an alternative to conventional methods to reduce the carbon footprint and gain relatively faster strength improvement, which is called soil carbonation. So carbonation is the process of introducing gaseous CO2 into the soil that is mixed with alkali following the traditional method. Through chemical reaction, this process precipitates calcium carbonate binder on the soil grains that can improve the strength and stiffness of the material. Phase 1 of this study has extensively investigated what are the factors contributing for optimum performance of this chemical reaction and how to gain maximum strength improvement. Based on those knowledge taken into account, we have designed a larger scale experiment to develop a method to carbonate soils for shallow subgrade stabilization. So this figure, what you can see here, this is a 2-meter long box that represents one lane of the roadway and 1 meter in width that represents unit length along the longitudinal direction, and the soil layer that is mixed 10% lime mixed soil, which is 300 millimeter thick, and the underlying untreated soil, which is compacted at the same density, and it's 150 millimeter thick. So the concept to introduce the gas is we introduce the gas at the center of the roadway when the roadway is covered with a regular construction grade plastic tub. So the gas will be introduced from the surface of the roadway so that it can carbonate a practical depth that needed for typical roadway stabilization. So the box is constructed with a silty material, and that material is classified as per STM is ML, which is highly frost susceptible material. And as the box was constructed, we also made some instrumentation, for example, thermocouples and bender elements to monitor the temperature changes due to the chemical reaction and shear velocity changes to monitor the stiffness to see the improvement that's happening instantaneously. So this figure is our overview of the overall soil carbonation experiment. After carbonation, we performed field California bearing ratio test to determine the strength improvement by carbonation. After carbonation, we take this box in a large environmental chamber to apply freeze-thaw cycles. The objective of this experiment is to evaluate the freeze-thaw durability, that is carbonated soil, under different freeze-thaw cycles. So in this figure, you can see we try to simulate a 1D freezing condition. That means the surface of the box was insulated, and we applied some hot air to keep the bottom of the box just above the 0 degrees Celsius, so that we can make sure the freezing front is coming from top of the rotor, which is normally happen during the field condition. And also we saturate the box prior to applying any freeze-thaw cycles and kept supplying water as an open system to create the most detrimental weather condition. So we wanted to see how under this condition, how the carbonated soil layer can perform. So for interest of time today, I will be presenting a very limited results to convey the key findings of this larger scale experiment. So let's dig into the results part. So this figure, what you can see here is the changes of shear wave velocity with carbonation time. Also, the secondary vertical axis is showing the total amount of gas that introduced into the box during carbonation. So the solid line with triangle is showing change of shear wave velocity at z equal to 50 millimeter, and the blue solid and dashed line is showing the changes in velocity at z equal to 250 millimeter from the top. So at 6 hours, after 6 hours of carbonation, we can see there is a sharp increase in shear wave velocity, which remains and which reached about 600 millimeter per second. So we can clearly see there is a significant strength improvement, and the value corresponds to a soil that represents very dense soil and soft rock. So this provided us a indication as soon as we introduce the gas, there is a obvious changes in soil property, and that is an instantaneous process. Now I would like to show the formation of binder content due to the chemical reaction. So this figure is showing us the calcium carbonate binder content along the depth. So our box had two sides, side A and side B, that represents two initial conditions, which is degree of saturation 30% and 40%. So I am just presenting one side of the results, but it is noted that we have observed very similar result on side B of the box. So as you can see here, the red dotted line, red dashed line, this is the maximum amount of calcium carbonate that can form based on the available calcium hydroxide. So from 0 to 150 millimeter, the soil is completely carbonated, but afterwards, where almost negligible amount of binder content formed. So meaning the top 150 millimeter was carbonated. And we also saw significant changes at 50 millimeter based on the shear wave velocity. So now I would like to talk about the strength profile of the material after carbonation in terms of field California bearing ratio test. So with the material rating, so 0 to 30 CBR represents the subgrade quality of the material, while more than 30 represents subbase quality material. So the black solid line with circles represents the initial one, meaning before introducing the carbon dioxide gas into the box of the compacted soil. As soon as we introduce the gas, we have performed two CBR tests at various depths from two different locations. And the red solid line is the average of those two values. So you can see here, there is a significant strength improvement from 20 to 60, and which is also reduces as we go deeper depth. So the material turns from subgrade quality to subbase quality with a very good to good rating. So that means carbonation improved the in situ properties of the soil very significantly, which is very encouraging. However, before we take into the box for applying freeze-thaw cycles, we soak the material, like we saturate the box. That soaking causes significant reduction in strength, as shown by this red diamond. So, which is completely aligned with the findings in the literature soaking has a significantly negative influence on CBR value. So after that, we have applied 2 cycles of freezing and thawing into our box to see how the durability of the carbonated soil layer can be. So same as before, here you can see the CBR profile with depth, but this time I am presenting the frost susceptibility rating of the material. Say for example, 0 to 5 represents very high to high frost susceptibility, while more than 20 represents almost negligible frost susceptibility. So if we remember, our material 0 to 150 millimeter was carbonated, and this blue line represents the CBR value after 2 cycles of freezing and thawing. So the untreated soil that we mentioned in the beginning of this presentation, which is called highly frost susceptible, also revealed from the experimental results. As compared to this, we can clearly see that the CBR value of the carbonated layer remains 15 to 20, which shows the frost susceptibility of this cemented soil is very low. So these results from this presentation is highly encouraging to make a comment that soil carbonation is an effective alternative chemical stabilization method that can be applied to stabilize shallow subgrade soils for any transportation projects. Also, this process consumes a significant amount of CO2 gas, which can reduce the carbon footprint associated with this stabilizing agent. So in summary, we can say that soil carbonation is an effective chemical stabilization. So without further delay, today I would like to thank TIDC for funding this research project and Advanced Structures and Composites Composite Center for their support in this largest experiment. Last but not the least, I want to thank my friend Danilo Botere Lopez for helping me with this large experiment. Without his support, we wouldn't achieve this success today. So thank you all. If you have any question, please reach out to our research team. We are more than happy to answer your questions. Thank you. Have a wonderful day.